Hello friends, welcome to our video. Today we're going to talk about weather forecasting models. Under our main topic, we'll explore the types of weather forecasting models, numerical weather prediction models, and model evaluation and improvement. Let's get started. Types of weather forecasting models. Weather forecasts come in different types, depending on how far into the future they go and what data they use. Weather forecasting is based on three main types of models. These types are 1. Statistical models. Second, dynamical models. Third, ensemble models. Statistical models. Based on historical data and statistical relationships to predict future weather conditions. These models are computationally efficient but may not capture complex weather dynamics. Dynamical models. Solve complex equations of atmospheric motion and thermodynamics. These models require significant computational resources but provide detailed and accurate forecasts. Ensemble models. Run multiple simulations with slightly different initial conditions to account for uncertainty. These models provide a range of possible outcomes, improving forecast reliability. We mentioned that weather forecasting is divided into several models. Additionally, these models are further categorized based on the time period they focus on. Some of the main models are as follows. 1. Nowcasting. Second, short-range forecasting. Third, medium-range forecasting. Fourth, long-range or seasonal forecasting time. 1. Nowcasting. This predicts weather for the next 0 to 6 hours. It's used for fast-developing weather like thunderstorms or fog. Nowcasting is essential for airports, emergency response teams, and outdoor events. It uses radar and satellite images in real time. Second, short-range forecasting. Covers up to 3 days ahead. This is the most common forecast we use. For example, checking if it'll rain tomorrow. These are usually reliable and are based on high-resolution weather models. Third, medium-range forecasting. Forecasts up to 10 days ahead. Accuracy starts to drop a bit here, but it's still useful for planning travel or events. Meteorologists use ensemble models to handle the uncertainty. 4. Long-range or seasonal forecasting. This predicts weeks to months in advance. It's not specific. You won't get rain on Tuesday, but it shows trends like warmer than average months or higher chance of drought. Farmers and governments often use these. Weather models. A weather model is a computer program that uses physics, mathematics, and real-time weather data to simulate the behavior of the atmosphere. These models help meteorologists predict the weather for the next few hours or days. Weather models take in observations like temperature, wind speed, air pressure, humidity satellite, and radar data. Climate models. A climate model is a computer simulation that represents how the Earth's climate system behaves over long periods of time, usually decades to centuries. These models help scientists understand past climate, predict future climate, and study human impacts like CO2 emissions. Climate models don't just simulate air or clouds. They also track ocean currents, ice melting, and CO2 levels, all connected in one system. Numerical Weather Prediction (NWP) models. Modern weather forecasting depends heavily on something called numerical weather prediction, or NWP. These models simulate the atmosphere using mathematics and physics. The Earth is divided into a three-dimensional grid like cubes in the air. In each cube, computers calculate temperature, pressure, wind, and humidity. They use real-world data from satellites, weather balloons, radars, and ocean buoys. Then, supercomputers process millions of equations to predict how the atmosphere will change over time. The more powerful the computer and the more data we have, the more accurate the forecast. Some of the most well-known NWP models include ECMWF from Europe, GFS from the USA, WRF, which is used for smaller local areas like cities or regions. Types of NWP models. ECMWF runs one of the most advanced numerical weather prediction NWP models in the world. Its forecasts are used by national weather services across Europe and globally. The ECMWF model includes 1. Global atmospheric and ocean models. 2. Data assimilation from satellites, weather stations, balloons, etc. 3. High-resolution grids for accurate simulations. 4. Ensemble forecasting to account for uncertainty. GFS stands for Global Forecast System. It is a global numerical weather prediction model developed and operated by the United States National Weather Service, NWS, specifically by NOAA, National Oceanic and Atmospheric Administration. The GFS model uses powerful supercomputers to simulate the atmosphere based on initial conditions from weather balloons, satellites, ground stations, aircraft, and ocean buoys. Mathematical equations based on physical laws, like momentum, energy, humidity. 3D grid system that covers the Earth's atmosphere, land, and oceans. WRF stands for Weather Research and Forecasting Model. It is a flexible, advanced, and customizable weather model used primarily for regional and local weather forecasting and atmospheric research. It works as follows. 1. Takes initial conditions from global models, like GFS or ECMWF. 2. Runs high-resolution simulations over a chosen area. 3. Includes land surface atmospheric physics, microphysics, and boundary layer schemes. Also, WRF, Weather Research and Forecasting Model, has several unique features that set it apart from other models. You can choose the area to forecast, e.g., a country, city, or mountain region. You can adjust the resolution, e.g., 1 to 12 kilometer grids for very local forecasts. You can simulate specific weather events, storms, fog, hurricanes, etc. Error analysis. Weather models are powerful, but they're not perfect. Forecasts sometimes get it wrong. For example, predicting rain that never happens. That's why constant evaluation is crucial. Meteorologists compare forecasts with actual weather observations to see how accurate the models were. They use techniques like error analysis, skill scores, ensemble forecasting, where multiple versions of a model are run with slightly different starting conditions. Artificial intelligence can analyze thousands of past weather events to help optimize forecasting techniques, improve precipitation forecasts, and reduce false alarms. This collaboration between human scientists and machine learning systems is making weather prediction more precise, reliable, and responsive.